Let's start today's lecture on Laplace transforms. Finally, we return back to whatever you learned in circuit before. And if you have any questions on the lecture or on the homeworks or on any technical issues, please ask them now. So Laplace transform, hopefully you remember something from circuits and remember that you used it as just given rules. You just taking some circuit, converting H capacitor to some weird formula with S, and then you're computing some other circuit stuff and doing something with that and magically get some correct answer, hopefully. So we will not talk a lot about that, we will just touch a little bit that theory. After all, you're doing similar things that you did with Fourier, and Laplace, generally speaking, could be thought as generalization of Fourier transform, because instead of j omega, you're using S, which is full complex variable now. Like something that you used S equals to j omega in Fourier, now it's more general and works with any complex number. And this helps us in other things, in other ways, not only to analyze signals, but also to analyze systems. And systems are a little bit more tricky in that sense. In systems, we will want to analyze stability later. I will just talk a little bit about that. It's in the next lecture, maybe in 2 lectures. And then it will help us to understand how those systems work, how to get transfer function of the system, how to get other important properties of systems, especially linear systems. So this is all included in Laplace transform, and we learn Laplace transform to understand how to analyze systems now. And this is the second part of the course. Now, in Laplace transform, you have only a few simple tricks which are used in solving all kinds of problems related to Laplace transform. The questions will be related to how to find direct Laplace transform using tables or without tables, or to find inverse Laplace transform, or to find response of the system of some kind, or to find maybe impulse response of the system, and other things like that. Now, Laplace transform also helps us to solve differential equations, ordinary differential equations, in a very simple, trivial, almost way, by solving polynomials instead of differential equations. So if you have any differential equation, linear differential equation, you probably already learned about those differential equations and a little bit struggle to understand why those exponents coming all over the place from nowhere. We'll just say, like, this is the solution, general solutions, and find coefficients to that differential equation, and things of that kind just coming from nowhere. So those things are actually coming from Laplace transform. Now we will see some examples of that too. Now I want to show you a few examples which are not really tricky, but just showing you the procedures that you will need to do in tests and quizzes and general questions on Laplace transform. So you have question of that kind. So you need to find Laplace transform of some given function, for example, x of t, which is equal to minus exponent 3t ut convolved with t step of t. Questions of that kind. Where you want to find Laplace transform, you're almost always using tables. In Fourier, sometimes people give you some graphical representations of the functions, and then you need to find it using integrals and other stuff. In Laplace, it's almost never the case. The only case where you can actually find Laplace transform by hand is for exponent, because this is the only easy case. Everything else, just computer can help you to really compute it from any other more complicated kind of thing. So you always need to think where I can use a table and which functions from the table I need to use in that case. So first of all, you have exponent in the table. So this is what you have in the table. That function is transformed to 1 over s plus 3. This is formula number 5 in the table. Also, you have in the table that from the linearity property, you can multiply both sides by -1, right? So if you multiply here by -1, this one will be multiplied by -1. This is linearity property of Laplace transform. Again, this is true for any integral transform, because integral is linear in that sense. Okay? So this is from linearity. Now, second one, t times u of t. You can use basically, let's simplify it a little bit. So you can write that thing as t to the power of 1, e to the power of -0 times t, and step of t. Now, why I'm writing that in that way? Because in the table you have t to the power of n, e to the power of -at, u of t. This is what you have in the table. Okay, you don't have t times u. So you're just finding specific case of that thing which equals to that one. Okay, obviously if this one equals to 0, exponent will be 1, and t to the power of 1 will be t. Right? It's the same thing. Yes?
On the first one, you put negative e to the -3, but in the function you wrote there is positive 3 to the 3t in the exponent.
Thank you.
All better.
So we are looking for convolution of actually stable functions.
So which formula is that? Yes, the t times the set function from the
I'm sorry?
from the table. Which formula?
So in the table you have something like that. You have t to the power of n exponent minus a t u of t, something like that.
Okay, so a is 0.
So a in that case is 0 and n in that case is 1. Okay, and then you have, for that you have transform, which will be n factorial divided by s plus a n plus 1. And this is formula number, let's see, number 6
Okay.
in the table. Now, in that case, n equals to 1 and a equals to 0, so it's 1 over s squared. This is what it will be. Now, you have alternative here. You don't have to use that rule in the table. You don't have to use that specific rule. You have also rule of property, which multiplies by t. So when you multiply some function by t, you can find transform of the function, and this will be basically adding derivative of the response. So let's see how we do that alternative. So alternatively, we know that u of t is transformed to 1 over s, which is step function is transformed to 1 over s. Let's see, it's formula number 3. Okay, and now multiplication by t. To the power of n. Okay, will be converted into -1 to the power of n dn dsn of transform of s. And this is formula number, let's see, it's formula number 4 in the properties. Now, obviously, t to the power of 1 will give us minus derivative of fs. So what is fs in that case? So what is fs? Big fs is this one. This is Laplace transform of that ft. And what is that ft right now?
ut.
U of t.
So your fs is 1
So
over
f of s is basically 1 over s.
Correct.
Okay, so what we need to compute t ut is transformed to minus, which is coming from here, d to ds of 1 over s, which is derivative of 1 over s. So what will be the derivative of 1 over s? Negative 1 over s squared.
Yep. Which becomes positive. Cool.
Because of the minus. So we get, of course, the same thing. Obviously, if you get something else, you did mistakes on it. Because both ways should give you the same result. Okay, and now all you need to do is define the transform of x of t, which is based on the property of linearity. So you have not on the property of linearity, on the property of convolution. So what is a property? So if the time domain is convolved, what happens to Laplace domain? Multiply. So we just need to multiply here. So we have two parts here.
1 over st plus 3s.
So you have one part here and one part there. You just multiply them. So convolution property, it's property 12 in the table. You just multiply those. You get times minus 1, that's plus 3.
It's not a really stupid question, but when we're working this out on the actual test, if we are given these questions, when you're doing the arrow with the number underneath, do you want us to write it like that so that we're showing you what formula we're using from the table?
It gives you advantage, especially if you make a mistake.
Okay.
If you're not doing any mistakes, then that's fine not to write it. But if you're making some mistake and then I just see that you used by mistake something else or in some wrong way, then you can get partial credit just for miscomputation or miscalculation or something.
Okay.
And it's much smaller reduction of points than compared to you just don't know what you're doing at all.
Okay. Thank you.
Okay, any questions on that? Okay, so down with the first one. Okay, another type of questions which is a little bit tricky is to find values of x at 0 and infinity. Which means you have some signal which is coming from the system, measured as input or output of the system, and you want to know what happens to that signal when it starts, and will it converge somewhere to some specific value? That's what you want to know. So questions look like that. Determine x0 plus x0 and limit of t goes to infinity, x of t. For x plus Laplace transform is given by some formula. In that case, let's say it's equals to that. Something of that kind. So you're given Laplace transform of maybe output of some system, and I'm asking where this output starts and where it ends. Obviously asymptotically, so it goes and stabilizes somewhere at some specific value. Now, the first one is easy because it's almost always defined, so you have some cost point. The last one is defined only when you have stable system and only when it gets to some specific level, because it might oscillate forever, right? And then you don't have any limit, so limit does not exist in that case. And you need to be very careful about that. You will learn in next lecture, you'll learn how you actually identify that this limit exists. This is stability of the system, and you cannot have more than one pole at 0. This is the rule how it goes when this limit exists. Okay, so let's start with the first one, which is easier one. you want to know x0 plus. This is given by the formula, which is limit when s goes to infinity. S times xs. This is final value. Okay, this is initial value theorem. You have that at the end of the table, Laplace properties. Let's put it in. So it's lim t goes to infinity of s times 7s plus 10 divided by s plus 2. So s is cancelled, and it will be what it will be.
Seven s plus 10 over s plus 2.
Yes. What is that limit or sorry, it's not limit of t, it's limit of s. S goes to so you want limit of s goes to infinity of 7s plus 10 over s plus 2.
7.
It's 7. Because this number could be ignored compared to that number, and this number could be ignored compared to that number, which is very big. So it's 7s divided by s, which is 7. Okay. Okay. Now how about x infinity? This is what you want.
Yeah.
Assuming that this limit exists, and again, we will need to check next lecture why this limit exists. But if it exists, then we will assume that in this one it exists because this one is in left semi-plane and this one is only single pole at 0. So it exists. This is very similar limit, but s goes to 0. Like that. Again, s is cancelled, and now we're looking for a limit where s goes to 0. And what will be the number? 5. How can we verify that this is true if we have time?
S divided by 2.
Hmm?
7 divided by 2.
How would you verify if you want to know if this is true? You completely correctly computed everything.
Put it back into
But what is the methodology?
Put it in.
Put in integral where? Which integral?
The interval.
The integral? You know about the integral that I don't know about. Can you tell me more about that?
Graph it? Graph it?
Graph it? Graph what? X of s?
The function?
Which function?
So what you're taking the limit of? S.
I'm taking limit of the function s times x
Yeah.
of s. But I'm asking, like, obviously this is Laplace transform of some given x of t.
Yeah.
I'm looking for that one, like how it helps me.
Do like the inverse.
I thought you were asking how you can tell that that's the limit.
Yes, how can I know that those are the correct numbers? Which will be in real x of t. Yes.
I think people are getting mixed up. Yeah, I think they aren't sure that you're asking that 7 is the limit instead of the 7.
No, I'm not asking if the 7 is limit
Yeah.
of that one. I'm asking how do you know that this is true? That this one equals to this one and this one equals to this one. And those are small x's, okay, those are x in time. Okay. T equals 0 and t goes to infinity.
Calculate or find the inverse Laplace transform.
Okay, so you need to calculate inverse Laplace transform of that thing. And you can check that directly. right? So inverse Laplace transform of that thing, I just computed for you. X of t, which is inverse Laplace transform, ILT. Okay, this is a shortcut. It's 5 step of t plus twice exponent minus 2t step of t. This is the inverse Laplace transform. You can try that at home to compute from that one to that one inverse Laplace transform, and you will check that this one is correct. You can use the table also. You have it in the table. Now, obviously, when t goes to 0, the step equals to 1, right? And this one equals to 1. So you have 5 plus twice exponent 2t. T is 0, right? So exponent of 0 is 1. So you have 5 plus 2, which is 7.
Okay.
This one,
Okay.
right? Now, when t goes to infinity, this is 1 still.
5.
And this one is 1.
Oh, yeah.
But this one is infinity, so it's exponent to minus infinity something,
0.
it's 0. So it's twice 0, and then you're left with 5. Okay, it works. That works. This is really impressive.
That works.
Okay, any questions on that kind of question?
Let me explain basic algebra.
Okay, let's try another example. We need to find inverse Laplace transform of some given function. So find inverse Laplace transform of something of that kind. Now, obviously you can use tables to get that, but you can do that in one case. In that case.
Whenever you say we can. Partial fractions. So what?
This is where you can't use the tables, unfortunately. And you need to show your knowledge of how you work with partial fraction expansions. This is part of the course. Again, not my decision, because I would drop the entire topic altogether, completely useless with computers. But in the test, we need to ask you some question, partial fraction expansion.
You don't have to. You don't-
Yeah.
I won't tell anybody.
You'll be like, yeah, I know how to do that.
It's not that difficult, okay? I will not ask you difficult questions on that topic,
There you
okay?
go.
I will not ask questions with complex roots and with many complex roots.
For some reason, I don't.
Yeah, just set kind of questions or a little bit maybe more complicated. And I will give you a lot of time to solve it.
No.
Okay.
Less complicated. Then we're good to go.
Yeah, it's easy.
Okay, so how do we start to solve that kind of problem? First of all, we know that we need to divide it in smaller parts where you have single root in a single addition. Like you want something divided by s plus 1 plus something divided by s plus 2. Okay, and that's exactly what you write. So you have even two methods to solve that kind of problem. So you solve it like that. You're writing it as something divided by s plus 1 plus something divided by s plus 2. If you don't have any complex poles, it will be always constant divided by pole, plus constant divided by pole, plus constant divided by pole, depends on number of poles that you have. Okay, always like that. If you have one of the poles has multiplicity more than 1, then you divide that into two parts. It will be like s plus 2 squared, for example. It will be b divided by s plus 2 plus c divided by s plus 2 squared. And so on. Depends on number, multiplicity of the poles.
That's case 2, right?
But this is the simplest one, this is case 2, yes. But this is simplest case where both poles are completely, they are real and completely different. Now, from now on, I'm doing common denominator, which is a little bit of algebra. This is method number 1. And in my experience, most students find set method the easiest one and not using the formula. I don't know why. Formula is much shorter, but whatever you prefer. Okay? So just doing common denominator to those two and comparing to the original one. Okay? All of the coefficients of the polynomials, two polynomials are equal only when all of the coefficients are equal. Right? We know that from algebra. So that polynomial will be exactly the same like this one because this is common denominator when I started with this one. So I need just to compare that polynomial with whatever I will have here as a function of a and b. And then I will have system of equations for a and b, two equations, two linear equations, which I need to solve. That solution will give me those a and b. So this is the overall process of how I find partial fraction expansion. So let's do that. So obviously here I will have s plus 1 times s plus 2, the same thing like here. But here I will have a times s plus 2, which is as plus twice a, and here I will have s plus 1 times b, which is b times s plus b, bs. Okay, now we compare the coefficients. What are the coefficients? So what is the coefficient of s here?
A plus B.
A plus b. What is the coefficient of s there?
7.
7. What is the coefficient, free coefficient here? Twice a plus b. This one and this one. What is the free coefficient there?
0.
0. That's it. You need to solve that system of linear equations and to find a and b. And those will be the numbers. Okay, how we solve that? You can do that with multiple. You can use matrices. You can use just direct Gaussian elimination. You can just substitute one variable instead of another one. You can say, let's say, b equals 7 minus a. And then from this one, you'll have twice a plus 7 minus a equals 0. Right? So twice a minus a will be a plus 7 equals 0. So a equals negative 7. And then b from the first one, you need minus 7 here, or you need here, so b will be 14. This is the solution of the system. So I can say that x of s is a, which is negative 7 divided by s plus 1, plus 14 divided by s plus 2.
That's all we have to do.
And now we need to do the transform, inverse transform. Because for those ones, you can use a, okay, for single form. Now, those are simple ones, just exponents. It's minus 7 exponent with z minus z value, and 14 times exponent minus z value, times step, of course. So you'll have something like that. It will be minus 7 exponent minus t, plus 14 exponent minus twice t, times u of t. This is the solution of the problem. But in my opinion, for that case, it's a very long solution. You can do it much shorter and faster.
I think it's easier to do it than we do it in the first.
And you can get to those two numbers easier. The same, you have that process the same, the last line. But this process of writing that thing, computing that thing, and then computing system of equations could be simplified a lot. All you need to do is just to put the formula for a and b. So how you remember that formula, how you use it. First of all, you have that in formulae pages, but even if you don't remember to look in formulae pages. All you need to remember, you cancel one of the poles, you just pulling it out, and then putting, instead of s, the number which will make the pole 0, the formula 0, which is minus 1. This is coefficient number 1. Then you're doing the same thing with the second one. You're pulling it out and plugging here minus 2 and minus 2. And this is coefficient b. That's it. That's it.
Can you write it on the board so I can write it down?
This is our alternative, okay? A equals limit where s goes to -1 of z pole s plus 1, which is the first one, times that thing, which is 7s s plus 1 s plus 2. Which means that those are automatically cancelled. So the same thing like pulling that out. Just cancelling that automatically. And then you get 7 times -1 divided by -1 plus 2. See? So you can get obviously -7.
So it looks like it's similar to the initial value.
Not exactly. In the initial value and final value, you have s always here.
Right.
Here you're multiplying by that p, s plus p.
And whatever makes it go to 0.
And here it's minus p always.
Right.
Okay, so it's switching each time you're taking single pole for which you compute as a coefficient. Because look, each coefficient associated with a specific pole, right? So this one is -1, this one is -2. So each one of them is associated with specific number here. So for that one, you pull in that one out. For that one, you pull in another one out, which is associated with it. If you have more of those, you pull in the associated one each time.
Right.
Why? Because if you are not doing that, obviously, if you put in that one here, you're dividing by infinity, right? I'm sorry, by 0. You cannot do this. You need to get rid of that somehow. And this is not explanation why you do this. This is completely different from proof, but this is a method. Okay, you just removing the pole, and then the rest you computing as at that point of that pole. And what will be the value of that function at zs? So it will be -7, and b will be limit s goes to -2, which is the location of the second pole, of s plus 2, and 7s, s plus 1, s plus 2. This one is cancelled now with this one. And then you get 7 times -2, -2 plus 1. Okay, so it's 7 times 2, which is 14, divided by 1. That's 14. And obviously get back to the same thing.
Outstanding. We have to use the other formulas when we do the case too.
Now, other formulas are a little bit more complicated. For example, if you have like double pole and you have a square of third power, whatever power, then it becomes a little bit more complicated because you need to compute also the derivative of that thing. So it will be the same thing, you cancel in the part that you don't want, and derivative, first derivative or second derivative of the formula which left.
The derivatives that we do, is it
Yes.
however many powers we have?
Yes, so number of derivative, like order of derivative equals to the powers that you have.
But it's just the derivative of xx, not the s the term itself. Like you
It's
have
a derivative of that
Right,
thing,
right.
yes. You have formula in the formula page for that too. So most people would really use that formula for simple case and use probably that approach for the other less simple case. Okay, because using the formula it will be tricky. You need to do basically derivative of rational function,
Yeah.
which is polynomial over polynomial. Not too difficult, but still kind of computation a little bit expensive. Compared to that, I don't know. You can choose your method. Any questions?
No. Yeah, those are pretty well fun.
Okay, let's talk a little bit about circuits. Get back to electrical engineering.
So,
You have something simple. You have x of t, you have resistor, capacitor, and you have y of t here. X of t here. This is resistor. This is capacitor. We can put some values in there. 1 kilo ohm. And capacitor will be 200 microfarad. Just to make numbers easy and beautiful. Why those numbers are easy and beautiful? Why they go together well? 201 kilo. Easy. Because we compute in RC, which will be basically 1 over RC, which will be 5. Easy to work with. This time constant is very easy to work with. So RC equals basically 0.2, so 1 over RC is 5. This one is basically 0.2 seconds, right? This is time constant of RC circuit. Okay, so what questions we have to find is find voltage across the capacitor. This voltage will be Y of t. For the input, X of t equals delta t. How would you call that kind of output of that system? One? No, the Laplace transform of delta is 1, yes. But what is Y of t? What is the name of Y of t, let's say?
It's the response.
It's the response of the system to the delta. And how we call the response to delta? No, this is not zero response. Zero response is 0 in that case.
It's a pulse, right? It's just like one.
This is impulse response, H of t. Remember from previous lecture? This is exactly what describes the entire linear system here. This is property of that system, H of t. H of t is impulse response. This is when you put here delta and you measure voltage here. Whatever the voltage is impulse response of that system. Now, in next lecture, you will learn that basically Laplace transform of impulse response is transfer function. And this is the most popular thing that you learn about systems in general. We work always with transfer functions. Transfer function of the system is Laplace transform of impulse response, nothing else. As simple as that. Now, we want to find that basically without using too much knowledge that we have so far, because we will have more of that kind of thing in the next lecture. But right now, you just want to find that thing. What is the response of that system to a single pulse, single delta spike? How would you solve it? How would you start it? First of all, you need some description of the systems that you're familiar with. What kind of description you could find for that system? What do you know on solving that kind of systems? I mean, we don't know how to solve that system.
You transform the capacitor into a source.
Something from electrical engineering that you learned in circuits. How you solve that circuit? I mean, you obviously solved that kind of circuit before, right?
Yeah,
Am I right?
We convert the frequency of it.
Otherwise, I'm concerned. If you never solving that kind of systems before. Okay.
It's RC circuit.
So how about Kirchhoff?
Yeah.
Familiar with that?
Yeah.
That sum of the voltages over the loop should be 0, something of that kind.
Yeah.
And the voltage on the capacitor is R times I, current,
Yeah.
Ohm's law.
Yeah.
Simple things. So we are not doing anything complicated here.
No.
Okay, so let's see. X of t minus y of t, what is that? This is voltage on the resistor, right? Now, what is the voltage on the resistor? This is basically R times I. This voltage on the resistor, right? Now, what is I? I is current through the capacitor. What do you know about current on the capacitor? When the voltage on the capacitor is Y of t.
It's the
No, it's changing, it's function of time.
yeah, it's
It's I of t. All of them are functions of time, some functions of time, whatever they are.
it's the derivative of the voltage
It's derivative of the voltage
times the
times c. So it's R times c d to the t y of t. This is the current through the capacitor, and this is obviously the same current which is flowing through the resistor, right? Now we have relation between y and derivative of y. Right, it's RCY, derivative of time. Okay. We have differential equation with input x and output y, which shows relation between all of those things. Right? Okay? So this is our differential equation. And just rewriting that, just moving y to the other side and dividing by RC both sides. Any questions so far? This is a differential equation which governs that kind of simple circuit. Now, obviously you can solve it in direct ways as we solved it before, but I want to solve it for x equals delta naught. And you obviously haven't heard about delta before, of course, right? Not in circuits at least.
No.
Okay, so how would we solve that kind of differential equation? I don't think that you want to guess the answer. It's not that simple. But you can do solution of differential equations using Laplace transform. And this is how you do generally that kind of equations. When you have differential equation, you solve it with Laplace transform, and then you solve it algebraically instead of using differential equation. So how you solve that with Laplace transform? Just transforming left part and right part separately. That's it. And then left part still will be in Laplace domain, will be equal to right part in Laplace domain. Because you're doing basically Laplace on that part and that part separately. They're still equal. Now, what is Laplace transform of y dot t? In the table. Of derivative in general. This thing that I recommend not by heart. It's just multiplying by s. Laplace transform of y. Okay? You have also a tiny thing here, which is y 0 minus, which is initial conditions. In that case, we will assume that y initial conditions are 0. But it could be some other number. Okay? Unless otherwise stated, this will be 0. Okay, next one. You have linearity, so you can multiply by any constant, right? So it's 1 over RC is still constant. Times Laplace transform of that thing, so this is linearity property. So you can add Laplace transform of the entire thing, is basically Laplace transform of this one, plus that one, Laplace transform of this one, because of the linearity, right? So you can take all the constant coefficients out, and I can separate sum or difference. Okay, and the last one. This transforms to 1 from the table, delta goes to 1, so it's 1 over RC. Now let's do algebra. You love algebra, right? No. So we have y here, so this one goes to 0. Let's remove this one. You have y here and y here, let's put them together. So we have y of s times S 1 over C equals RC. So let's put all these numbers in. So this one is 5, and this one is 5. So y of S equals 5 divided by S plus 5. And you're supposed to know what is inverse Laplace transform of that thing. This is exponent times 5. This is output. This is basically h of t. Impulse response of the system. That specific system. Looks like going exponent down. Any questions? Okay, how about solving the system for completely different x? Now your x will be x of, let's say, x of t will be something else. I want response to exponential input instead of delta. How will you solve it? Exactly the same way. You have that already, right? Instead of delta, you're putting that thing now. Now, that thing is transformed to Laplace. What it will be? It will be 3 over 5, and then
S plus 2.
S plus 2.
U, T, not work.
So it's in time. This is in Laplace. You're putting it here. So 1 over RC is still 5, right? And this is why you have 3 over 5 to make it easier to compute. So y of s, here instead of that thing, I'm putting just that thing. You have, that's more steps. So you have s times y of s plus 5ys equals 5 times 3 over 5 on s plus 2. So 5 is cancelled, you get 3 s plus 2. So y of s, again algebra, you'll have 3 over s plus 2, s plus 5. This is what you get. And from that one, inverse Laplace transform using the table, maybe it's number 10. Again, when you don't need to do partial fraction expansion, just don't. It's a bad idea if you will start doing that now. I'm not asking you to do that. Pay attention to the question. Okay? Now, that question you don't need to do it. What you'll get is negative 3 exponent minus 2t plus 3 exponent minus 5t divided by negative 3, which is cancelling all of those. And then you'll get exponent minus 3 minus exponent minus 5t. Should of course multiply it instead of function. This is my response of my my response, system's response to that kind of exponential input. Questions?
You say you use number 10?
Yes, formula number 10, where you have here a times exponent minus at.
So it's 2 minus 5 over 2.
So 3, this 3 comes from here, right?
Right.
And it's also, like you have formula for 1 over s plus something, s plus something,
Right.
right? And I'm writing the formula times 3. And here this is the b minus a, so b minus a is basically 5 minus 2 is also 3. And this is why initially I gave that as 3 over 5. That will be more convenient and you'll get to more simple expression. And generally, this is basically a good rule for all the tests. If you see that your answer looks simple enough, it might be actually a correct answer. And this is not saying that this is correct answer, but it means that something went right here. Or you just got lucky.
Or so complicated and uncomplicated itself.
Okay, and the last example for today, where you have double pole, with multiple poles at the same location. You want inverse Laplace transform of that kind of x. This will be, let's see. Again, using it's called PF, partial fraction expansion. Okay, so first step, always to write it in the correct form. What will be the correct form?
A over S plus 1 plus
A over s plus 1, b over
S plus 2.
s plus 2,
C
and c over s plus 2 squared. Now again, the same thing, common denominator. So here I want to have the same thing, s plus 1 times s plus 2 squared. And here I need to do common denominator. So it's a times s plus 2 squared plus b s plus 1 s plus 2 plus c s plus 1. Right? I'm just multiplying this one by that part, this one by those two, and this one by this one. Because this is what they are missing in their denominator. Okay, so let's simplify it. So let's see what we have. S squared times what? So you have s squared here times a in the first one. You have s squared here times b. So it's a plus b. And nothing else multiplies s squared. Now s is a little bit more complicated. So where you'll have s? So you'll have, here you'll have twice s times 2 times a.
Yeah.
Right? So you'll have 4a. Is it clear where I got this from? So it's the square plus 4s plus 4. Right, this one. Okay, so you have, is that 4 times a? From here we have, so it's s squared plus 3s plus 2, right? So here we have plus 3b and plus c. And now free coefficient. What is left is a times 4 for a. From the second one, twice b, and plus c. And now we have system of three equations. And here is of course the same thing. So the system of three equations will be a plus b equals first coefficient, then 4a plus 3b plus c equals, and then 4a plus 2b plus c equals. What will be the first one?
0.
0. Okay. What will be the second one? 3 and 4. Those are the coefficients here, so it's 0 times s squared and so on. So we need to solve it. Kind of tricky. You can simplify it to two equations because you can replace every b with minus a or every a with minus b, whatever. So let's see. So a equals minus b, right, from the first one. So let's put it here. So it's 4a plus 3b is the same thing like 4a minus 3a. So from the second one, you get a plus c equals 3. And here it's 4a minus 2a. So it's twice a plus c equals 4. Now you need to solve that one. This is a system of two variables. So a will be 1 and 2, right? And c will be 2. So 1 plus 2 is 3. 2 times 1 is 2, plus 2, 4, yes. 1 and 2. And then from those two, b equals -1. Now, don't forget the last step, which is putting it all together and finding actual transform. Partial fractional extension is fine. You need to find the transform, inverse transform. So you have a, which is 1 over s plus 1, b, which is -1 over s plus 2, and then plus 2 over s plus 2 squared. And then you're finding inverse of Laplace transform. 1 by 1, so you get sum of two exponents, and then t times exponent. So we get e to the -1t those two are simple, and this one will be trickier. This is our s of t. Questions?